Hello and welcome to Also Interesting. My name is Ali Hackalife and this episode will as well be entirely in English. Joining me today is the computer scientist Andrew Barto. Most of you may know him from his research in reinforcement learning, and last year he got the Turing Award together with his colleague. And I'm so happy to have you here. Hello, Andy.
Hello. Well, thank you for inviting me. Pleasure to be here.
You were born in 1948 and you worked for over 40 years in the field of reinforcement learning.
Yes. So I could describe my history a bit if you would like.
Yeah, very much.
So indeed, I was born in 1948. My mother was an artist and a nurse, and my father was a mechanical engineer. I became interested in things that led me to computer science eventually, but there were no computers except very large computers back in those days, and so I was basically raised to be a mechanical engineer. I was interested in machines of various kinds, motors, pumps, engines. I understood electricity to some extent, but never electronics. And actually, to this day, I'm not particularly interested in computers as machines. They're sort of the ultimate machine, but they don't have gears. They're not interesting to watch as they work and so on. It's all invisible. So it was a long route into computer science, which I can get into if you would like. But I still have the mentality of a mechanical engineer, and not really not a computer scientist.
Mm. When you started working in the field of computer science, first of all, you came from mathematics, right?
As an undergraduate, I studied mathematics, although I started my undergraduate career in the School of Naval Architecture at the University of Michigan. But I dropped out of that after a year, and I had taken all the introductory mathematics courses, so it was a natural move into the math major. I became disillusioned with naval architecture for a variety of reasons, but mathematics really, I was relatively good at it. I don't consider myself a mathematician by any stretch of the imagination, but reasonably good at it, and I found it really challenging and interesting. So my degree as an undergrad at the University of Michigan was in mathematics. Along the way, I did become interested in computer science-related subjects, and I applied to the graduate school at Michigan in computer science, and they accepted me. So I continued at the University of Michigan until my PhD in 1975.
Around that time, there were a few very field-defining books, like the one from Douglas Hofstadter, Gödel, Escher, Bach, or Brains, Machines, and Mathematics from Arbib, which tied together the idea of computers and mathematics as tools to understanding and learning. And
yes,
both of these books are quite influential on my own work, and they really defined how I started thinking about thinking. So it's a very interesting time to me personally, because it's the first time that the academia started to break out and to see the potential besides calculations in computers.
Yes. So yes, I mean, I think your trajectory is not unlike my own. I started earlier, and actually the book that really got me started was a book by Ross Ashby called An Introduction to Cybernetics. And I discovered this book, I think I was in high school, and I was curious as to what cybernetics is, and I read this book, and I could understand most of it, and it was really intriguing. So I really started reading various things related to cybernetics, and the book you mentioned by Michael Arbib was an influence on me as well, Brains, Machines, and Mathematics, which was great to combine those three subjects. And in fact, I think it was that book that introduced me to McCulloch and Pitt's work relating neural networks to logic. And that was, I think, really the work that it was extremely interesting. And that really is why I went in the direction of computer science, because in the computer science department, it was not called that then, at Michigan, they were interested in biology and evolution and learning. And those subjects became fascinating to me.
I think it's one of the subjects that fascinates humans, as long as we can talk to each other, how we learn and why we learn and how we teach and how we understand. And I think it's quite reasonable that in a time where computers changed from being room-filling objects to smaller and smaller things like the first pocket-operatable calculators from Texas Instruments and so on, I think it's quite reasonable to think that now we have the tools to improve on quote-unquote mechanical thinking.
Yeah, so I agree completely. Very, very nicely said. So as I said, though, the computers as machines didn't really didn't strike my interest, because the machinery was hidden, in chips and microelectronics. But I did learn to program. As an undergraduate, I took a few courses where I learned the Fortran, which was the prevalent machine computer language back then. In fact, as a graduate student, I was a teaching assistant for their Fortran course, and I think I taught a section. So I did learn to program, but I really didn't like doing it. It made me obsessive with regard to detail. And I couldn't sleep at night after working on programming assignments. So I've never really been, through most of my colleagues and friends in computer science have had periods where they've been programming intensely, but I never did that. And possibly a deficit to my set of skills, but I just I guess I didn't like having to deal with such minute details.
When you mentioned Fortran, actually today, one of the few software developers I know who got rich from just working and not founding his own company. He is a 30-something-year-old Fortran developer, and banks are paying him thousands of dollars an hour to just look at their old code, because there's nobody around anymore to find potential bugs and to fix it.
Yeah.
And on your statement about keeping you up at night, for me, programming was a key to telling the computer how to think the things I would like to think. And I like the quote from Steve Jobs about the computer being a bicycle for the mind. And so it helps you get around even more. It is an efficient way to bring your thoughts to make some distance. So I really know what you meant when you said you became quite obsessive about details, because that's what keeping me up at night way too often. But back then, programming seemed to be a way harder task. Nowadays, I can literally ask anything, and either the internet or a large language model will answer me. Back then, it seems to be way harder to just get started.
Yes. Oh, I agree. Yeah, that's completely true. So I guess I, having grown up being fascinated with machines, that is physical machines whose workings I could see and play with, uh, and I, I I thought of algorithms as machines. I still do. I think of algorithms as machines, very much like a clockwork kind of system. And so I was thinking of algorithms more than the machines that they were executed on, because that to me, I certainly did learn computer architecture and the basic ideas of how computers work, but the details were never of great interest to me. And so I was using them as tools, but not as a subject to study per se. So my work in computer science didn't go in what we called then maybe the systems direction. So, more advanced programming, operating systems, and so on. I didn't go in that direction. I went in a direction that was basically applied math, I guess, and algorithms for optimization and search and classification and things like that. So I missed out on the whole advanced real computer science that many of my colleagues really became experts at.
Mhm.
So I'm not really. I'm an atypical computer scientist, I think.
I would say one can agree on that, because you truly are computer scientists, but maybe the atypical one. So when you joined the biology department to research on learning, what was your field like at that point, and where did you start that? Because we all are on the shoulders of giants, and as you say in many of your lectures and talks, there were already ideas about pleasure and pain by Alan Turing, for example. So the idea that learning has some implications that we can think about or even model, these ideas aren't new, but somewhere you picked them up and you made your own theories on them. So where was the field when you discovered it?
Well, so gosh, that's a tough question. I think throughout my undergraduate, as an undergrad, I became interested in neural networks through the work of McCulloch and Pitts and logic and the equivalence that they established, which I found really very exciting to combine those two subjects. And but as a graduate student, my research was on cellular automata rather than biology. I was interested in, I guess, any kind of mechanism where a very small, let's see how to put it, a small specification of a system that could, through operation, generate a very complicated behavior. So this mismatch between the specification and behavior, which is very clear in cellular automata, where you just specify a local transition function, it's replicated throughout the collection of these nodes, and the behavior can be very, very complex. So my thesis involved cellular automata and harmonic analysis, Fourier analysis, spatial Fourier analysis on configurations of cellular automata activity levels. So that was, very indirectly connected to biology. It didn't involve learning. I was always interested in learning, but I didn't really do deep study of that until later, when I heard of a postdoctoral position available from the University of Massachusetts. One of the PIs of this project was Michael Arbib, who'd written Brains, Machines, and Mathematics, and which was very influential for me. So I applied for this postdoc, and I got it. And so I became the postdoc working on a project that was whose goal was to investigate a hypothesis about how neural networks worked. And it involved learning. So I really entered that area by virtue of this postdoctoral position. And that was the beginning of what became now reinforcement learning. I was a postdoc for 5 years, which was a delightful period of time. I didn't have to teach. I really wasn't even, it wasn't even necessary to write papers. It was an exploratory period that was really, very rare and extremely wonderful period. And in that period, Rich Sutton, who was a co-winner of this Turing Award, he joined as a student, a graduate student, and joined me in this project. I eventually became his PhD advisor. So he was my first PhD student, but we had worked together for a number of years and really, built this subject that's now called reinforcement learning. One of the things we were able to do was to really look at the history. Our objective was to see if these ideas, the main idea was that neurons are goal-seeking agents and that the brain is a society of goal-seeking agents, namely reinforcement learning agents. And we were supposed to see if this made any sense. Is this worth studying? And so we went and we looked very widely at the history and concluded that, yes, it was very interesting and actually, had historical precedents that we learned about. But the field had been neglected. And so we kind of rediscovered many things. Rather than inventing from ground zero, we were building on previous work that was really neglected in favor of more symbolic approaches to artificial intelligence. And even in neural networks, the learning rules were not reinforcement learning rules, but rather supervised learning rules. And we spent a lot of time trying to figure out, well, what's the difference between reinforcement learning and supervised learning? So, that was just an exciting period and rare, very valued by me. And, that was how this what's now called reinforcement learning became something that's quite well used these days.
When you describe this period of a few years working only in research without the other obligations, that sounds really like a dream for many researchers I know, because nowadays they are under high pressure to publish, to teach, to do university tasks.
Yes.
A wise man told me in one of his lessons, actually it was you, that supervised learning means learning with a teacher, while reinforcement learning means learning with a critic.
Yes. Of course, we borrowed that term from Bernard Widrow, who had developed the LMS learning rule, or the Adeline neural unit. And he did one study where he called it learning with a critic. And so that's where we got that name. And indeed, you're exactly right that learning from examples or learning with a teacher is different than learning from a critic. A critic doesn't need to know what the best output should be. You can criticize things without being able to create the things you're criticizing.
Mm. And bringing the critic to the loop of learning and understanding made the foundation of the reinforcement learning.
Well, yeah. So that was we wanted to see if these ideas were worth pursuing, and so we did apply a reinforcement learning system to certain classical problems. One of which is the pole balancing problem, which is a classical control engineering problem, and it was tackled by a number of groups, including Widrow, who did a system to learn how to balance what was a supervised system. And then Donald Mickey in England did a reinforcement learning approach to it. And we tackled that problem in the hopes that we could surpass the behavior of that we could surpass the performance of these previous systems. And so that was just to illustrate what these reinforcement learning systems could do. Mm-hmm. And so we were always looking at history and trying to build on that and to use as conventional terminology as we could in order to make the subject respectable in engineering terms. So that was my interest more than the interests of some of my students. But I really wanted to embed all of this into the historical context. And actually, in our book, you can see the sections on history, which I always regarded as being very, very important.
Yeah, I really value that most of your talks you gave over the last years that are online, they start with a short history lesson to demonstrate that a lot of things were already studied and discovered, and you tied them then together so that it's not the genius ingenuity of a single mind, but actually many minds working together.
Oh, yes. I mean, I think most of what we did had antecedents historically, even before computers existed. So I think in some of those talks, I talk about these electromechanical devices that were built to illustrate learning with relays and magnets and things, and not computers. It was much later that digital computers came on the scene and made things.
You might want to get that.
Okay, it's not telling me where it is. Okay, it stopped. Sorry about that.
That could have been Stockholm calling.
Oh, no, I don't think so. This Turing Award, I was, Rich and I both were totally surprised by this. We had no idea. And, I'm very honored and obviously pleased to see this obscure subject that we started on being recognized widely. And so that was extremely, very, very rewarding thing to happen. But it was a total surprise. And, we're very grateful, obviously. So I got an email from a professor I know who said, she'd like to do a Zoom on something, and we arranged a time, entered the Zoom, and it was a room with about, a dozen people, and they said, you're getting this award, and it was just took a while to absorb that that announcement. So it was a surprise.
I can imagine that. I mean, the award winners list is a very short list of people who did really impressive things like the RSA secure algorithms and so on, or the development of the language C. So really ground laying foundational work. And from my perspective, your work in reinforcement learning fits perfectly in there, but I can understand that it's quite overwhelming to get honored with these awards.
Oh, yes. I think one of our strengths was persistence. I mean, because we had, worked on these ideas for years, and funding was available, but there were periods of time when it was not available, and that didn't change what I was interested in, whether it was, funded or not. I didn't change my interests based on the availability of funding. I mean, there were periods when my students needed to be teaching assistants rather than research assistants because I didn't have funding. It was driven by fashion. I think in AI in particular, certain things are fashionable, and there are periods when fashions change, and so there were periods when what we were doing was no longer fashionable. Then it became fashionable, and then maybe not, and then maybe again. So these sort of cyclical, but I tried to be immune to the fashions. I've never really wanted to be driven by fashion, and so we were persistent. And I think that's true of Jeffrey Hinton also, who persisted on the problem of getting multi-layer networks to learn, and pursued that for many years in the face of skepticism. So, and we can see the results of that now with all of these utility of deep neural networks. So I think persistence, and it's hard to be able to do that when you have to depend on support. So I think I was very lucky to have periods of time without demands for publishing and so on. I should also say the students, my students, who came to the University of Massachusetts, wonderful students. I mean, much of this is due to the brilliance of graduate students that worked in the lab. So it was, this award went to Sutton and I, but there were others who contributed heavily to this whole subject. So I try to acknowledge them in talks.
When I looked through your list of publications, I was surprised how many names I already knew and how small the field still is, even with all you said it's a trend, or so that or fashion. You said that AI is right now in the talk of the town, but honestly, those who made the foundational research, they are not such a big group.
Yeah. That's true, I think. I just was talking via Zoom to a young person who is in graduate school studying AI, and he went to the big meeting in San Diego, the machine learning meeting, and it was 30,000 people at this conference, and that's mind-boggling. So that was, I mean, in my day, there were not venues for publishing things. I mean, we did write papers, but there was no proliferation of journals. We published in IEEE System Man in Cybernetics, the name cybernetics, of course, is key. That's really what fascinated me in the beginning. And there were other venues, but now there's dozens and dozens, and it's quite. I'm retired. I'm very glad I retired. I wouldn't have the energy to keep up with things. In the old days, we knew, everything that was being done in the related area, and now that's impossible. So not just for me, but for young students too. So it's a very, very different world in terms of the research environment.
Back then, when you started discovering this field and making your first progress, the topic of machine learning and machines being able to improve on themselves was the interest focus of, I would say, some scientists like you. A lot of hippies, like what was his name? The Whole Earth Catalog from Stephen Branson, I think. Or I'm a bit afraid confusing him with Stephen Bannon, other guy, but well, so Stephen Branson with the Whole Earth Catalog, the hippies, they got interested in thinking machines and the military. Did you manage to stay the whole time within the academia, or had you interests from the outside, like the military for guiding systems and so on, that funded your research?
Well, actually, the original research was funded by the Air Force Office of Scientific Research, which was basic research that, was funded by the military for potential applications. And that was our initial funding. That was the source of funding for my postdoctoral position. And, later, the National Science Foundation provided funding. But we were not pressured to, the project, one talks about deliverables. If a project is supposed to create something that's to be delivered at the end, a device or an algorithm or so on. And in our case, the deliverables were reports, recording what we had learned, and not devices. And that was, a rare possibility that was, I really appreciated. But, it was funded for potential applications. But we were not doing applications. We were doing basic investigation of the ideas. And so, it was a rare opportunity. And I have to thank so many. Well, you mentioned Michael Arbib. He was the PI of this project. And he was a professor at UMass where I was a postdoc. He championed me throughout the years. I became an associate professor. I became a full professor, and much of those possibilities were facilitated by Michael. His work not only got me interested in the field, but facilitated my development as I continued studying these things. So. Yes, I lost the thread of what we were talking about, but
I'll just keep it up from here, because when you said they didn't expect real-world applications from you, there are nowadays some real-world applications where reinforcement learning is part of everyday running algorithms. For example, self-driving cars, stabilizing airplanes, and so on.
Yeah.
Back then, when you started thinking about it, building the first idea frames for it, had you any application in mind when somebody asked you for an example? What could it do? I mean, the pole balancing is an interesting feedback loop and overshoot problem, but I mean, that's just one of the possible applications. So had you an example back then in mind that you told people throughout your research what it could benefit?
Well, I think we were always focused on control. Because reinforcement learning is basically a control problem. And we chose certain examples to illustrate these algorithms, and one, as I mentioned, the pole balancing, which had been done by others, and then one of my students focused on elevator dispatching, which is to organize how a multi-elevator system most efficiently serves customers in a multi-story building. And so he applied reinforcement learning to elevator dispatching. And so that was an example. And I talked to a lot of control engineers over the years. I guess I never devoted myself to a single application. And I know these days, as you mentioned, there are lots of instances of reinforcement learning being used. The one that's particularly interesting to me is in robotics, where the amazing robot movements that we see now with, say, humanoid robots, I think in many cases those are acquired through reinforcement learning. And that's a very, I mean, I was interested in motor control also, how our bodies control our movements. And so the idea of using RL for robot motor control is a very interesting application to me. So I don't know the details of all of these applications, but I know that in many cases they're based on reinforcement learning with a simulation of the robot instead of learning with the real physical machine, but with a high fidelity simulation. Reinforcement learning can work much more quickly and without the risk of damaging the physical machinery. So I think many of these applications are done through simulation.
Just a few weeks ago at the CES, the company Boston Dynamics, they unveiled their current Atlas model, a walking robot that's capable of carrying things. And one could say it's just an advanced pole balancing machine. But to be fair, they mentioned how many million hours they trained the movements to be that precise. And that's only feasible if you have virtualization of your robots.
Yeah. So actually, I know the Boston Dynamics. Actually, one of our students is a key person at Boston Dynamics who has been working with Atlas. And
as I said earlier, the field is not that big.
And they're using RL. And one of the classical problems with it is that you typically need lots and lots of trials. And as you mentioned, so doing it through a simulation makes it feasible. But so, many people are working on, well, how do you speed things up? That's a key problem. I guess my view of that is that in nature, evolution is an outer loop of adaptation that prepares the agents to learn quickly on the basis of prior structure and prior tuning to be receptive to learning for specific environments. So evolution and reinforcement learning are very similar processes. They work together. In fact, part of my interest came from being at the University of Michigan, where John Holland was a member of he was one of the PIs of the research group that I was funded by as a graduate student. But he is the person who created the idea of a genetic algorithm, an optimization algorithm based on ideas from biological evolution. And so that was fascinating to me and actually formed a basis of some of our early reinforcement learning systems. So we're really thinking of these stochastic search methods akin to genetic algorithms that Professor Holland and his students had worked on at the University of Michigan. So I was in that environment. I was very intrigued, and I always wanted to do something like a genetic algorithm, but with a neural network. And that led to some of the early work we did with the stochastic neuron-like units that would search and get feedback in terms of some performance index to eventually converge to something that scored highly, not unlike a population in a natural environment. So that was all sort of motivation for some of the things we did. And actually at that time, one of the popular subjects in what was the idea of an associative memory network. For example, Hopfield network, where you can take a collection of keys and what their output should be, and form a neural network that will a content addressable network. I'm losing my voice now, but what we did was instead of knowing what the desired output was, we had the system search and eventually converge to what the output should be, but not having been instructed, but rather doing trial and error learning using stochastic units. And that was motivated by genetic algorithms, the work we had been doing on reinforcement learning, and then the associative memory networks. So I think some of our earliest publications, I don't remember where it appeared, but we talked about an associative search network, which was really a reinforcement learning network that would end up doing what an associative memory network did, but learned how to do it without the instruction of what the associated patterns should be. So again, that was a combination of things that existed: genetic algorithms, associative memory networks. It was a synthesis. So I don't think I did anything that was really new. All of these things had precedence, but what I was able to do, I think, is combine them in different ways.
So about something maybe a bit more philosophical, I was on a longer walk with a good friend of mine, Michael Seemann. He is a computer scientist philosopher, so he studied philosophy and computer science, and he made his PhD in the era of platforms and the power of platforms, and like big organized networks. And we talked about the thing that's the reward giver. So in a simulated system, I know that the reward given to the agent is something I set in first place. And in a real world experiment, like training a monkey, for example, we can see that the dopamine release is tied to the learning. And in ourselves, dopamine is an important role when we talk about the positive reinforcement and understanding and learning. And we talked about it for a longer time. And then I asked him that I have no idea who's the higher agent in ourselves that will reward us with dopamine if we're doing good. And if that's maybe it's a bit esoteric or spiritual to say, but that there's an inner fundamental understanding of doing good for oneself and for others that's automatically rewarded by our brains. would you say that's too spiritual, or would that align with your research?
Well, no, I agree. But I think it's clear that evolution has provided us with reward functions in our brains that have served our ancestors through the evolutionary process. So there's there are two optimization processes working together. One at the evolutionary level, and then the other one at the behavioral level in individual organisms. So I think the whole problem of deciding what the reward function should be is a very difficult problem. And in simple examples, it's clear. If it's a game of Go or something, if you win, there's a reward. But in other more complicated types of situations, it's not so easy to specify that. But I think in the case of animals, there's been eons of evolutionary adjustment based on the fitness, the survival of the organism. So it's very similar to a reinforcement learning problem, but at a totally different level. So I think that's where our reward systems come from. And actually, we did some studies where we did search. We did a search in a space of reward functions, and the effectiveness was determined by the behavior of the agent using the reward function in a certain type of environment. And so we published a couple of papers on this, and it was surprising that it was difficult to intuit what a good reward function should be in a particular type of environment. And so there's not a straightforward mapping to reward. It's a difficult problem, and I think it's a key problem if people are worried about alignment of AI systems, and if agents are released in the physical world that are reinforcement learning agents, it's not clear. Sometimes agents will come up with things that are unexpected. And could be, or not only unexpected, could be dangerous. So I think that's actually a problem with optimization, not just reinforcement learning. It goes way back. Norbert Wiener talked about this, for example. And if you're doing optimization, it's kind of an indirect way of specifying what the result's going to be, but you don't know a priori what it's going to end up with.
Be careful what you wish for.
Yeah, exactly. Yes. And it's like, King Midas, right, who wanted the golden touch, and eventually his child turned into gold, and so on. So yeah, you need to it's a non-trivial problem. So
when you mentioned different reward functions, back in 2024, there was a study made on the release of oxytocin, which is one of the hormones that makes us social animals. And the research started out with the question that many people feel loneliness, and if there would be a medical way to make them feel less lonely. And I thought it's one of these optimization problems, because I understand where they're coming from. We have a loneliness epidemic over here in Germany, many old people losing their friends and contacts, and to cure their loneliness, having a pill would be probably beneficial to some, but would be a huge risk to all others. And I think about that actually a lot, because they discovered that there's no known mechanism to release the same amount of oxytocin than to get a back scratch from somebody else.
That's very interesting. I hadn't thought about that.
And you can't even fool yourself by scratching your back with a device. So you need another human scratching your back. And reading that and thinking about that, I think it's important to acknowledge that we are just some kind of social animal and not just a brain in a jar.
Yeah. So, no, I agree completely. In fact, I mean, there's a lot of work being done on multi-agent reinforcement learning, which really does deal with social interconnectedness. It involves game theory and other things, but I think the social part of intelligence, and in fact, I think you could argue that our intelligence really it evolved in a social context. So an intelligence that is not embedded into a social context would be a very different kind of intelligence.
I think there's only a very small group of people who would only help a child because it helps the economy on the long scale. So back on being social animals, there's a great book called The Experience Machine about the brain. And when you said you're coming from a mechanical background, would you agree with the hypothesis that the brain is an experience machine and that its operations are learning, so everything we're doing is tied to learning?
Well, I think we have a collection of innate behaviors that have persisted throughout evolution that form a substrate for learning. So I don't think everything is learned. I mean, we're animals that are the result of evolution, and so there are many built-in things. But on top of that, we learn from our experiences. I know that I saw the title of that book. I have not read that book, but I should read it. A multi-agent RL is a very interesting side. I never really pursued that because I thought it was too hard. Gets into issues that are very subtle and complicated. So I kind of stayed with the simpler case. But nowadays, people are pursuing the multi-agent case, which is it was the original motivation that the brain was a society of hedonistic neurons. And that's certainly a multi-agent scenario.
I really like the analogy of the brain being a society, because like in a democracy where not one single vote can be tied to the outcome, not one single neuron can be tied to a single thought.
Yeah. I'm losing my voice.
Okay, so let's wrap that up. So one last question, if your voice gives it.
Sure.
So when I contacted you, you told me that you're retired now and you aren't in the field of LLMs. And I think that's totally fair. And you did tremendous work to the field of artificial intelligence. What are thoughts and things that keep you up nowadays besides academia?
Oh, gosh. Politics. I mean, certainly in the U.S., we're going through some really horrendous changes.
I heard about it.
And so that keeps me up. But also health problems. I'm getting old. I'm challenged. I can't walk. So there are things that are challenging in that way. My house, I've worked to make it accessible to me, and so those things are occupying more of my attention than I would like. But And I read things that strike my interest, but a very eclectic collection of things, not all related to cybernetics or AI. My knowledge of current AI really is at the level of it's not a professional. It's really I'm reading mainstream media talking about AI. I've read some of the papers, but so I'm not keeping up with it in any kind of detail, and I'm glad I don't have to, because it's just it's a there's too many people doing too many different things. I don't know where it's going to end up. I do worry about the influence of social media and large language models on society, on politics. It's so easy to create erroneous images and so on. So all of those things. But many people are concerned with this, although many other people are eager to make a lot of money on these systems, and that is I think that's a real problem. So what keeps me up at night?
I see that there are many topics that occupy your mind.
Well, and just physically, that's that is intruding into my mental life more than I would like. Yeah. So no, it's been a pleasure talking with you, and I appreciate your perspective on a number of these questions.
It was very insightful. Thank you very much for your time, Andy. I can't tell you how big of an honor it is. I told you at the beginning that I'm quite nervous about the conversation. And now at the end, it just feels like a friendly chat with a fellow nerd. And that makes me very happy.
Okay, well, I'm very pleased to hear that. Yeah, so I enjoyed talking with you. So thank you for inviting me. So good luck in whatever you do.
Thank you for joining the show. Have a good day. Goodbye.
Goodbye. Thank you.